Hi, so today we're going to be talking about the electric flux and Gauss's law. So starting off, we know that the strength of an electric field is proportional to the number of field lines per unit area. And this number of electric field lines that penetrates a given surface is called an electric flux, which we denote with this Greek symbol. The electric field can therefore be thought of as the number of lines per unit area. So now we can look at this surface we have that I've drawn here. We can define this vector A as area multiplied by the unit vector, the normal unit vector, and we call this the area vector. It has a magnitude of the area of the surface, and it points in the normal direction of the surface. So if the surface is placed in a uniform electric field that points in the same direction as the normal vector, so perpendicular to our surface A, the flux would therefore be E dot A, which is E dot the normal vector, then the magnitude of A, which is just EA. However, if we look at this example where the electric field actually makes an angle of theta with the normal vector, so this angle theta, then our calculation would be different, where the electric flux again is E dot A, but this gives us E A cosine theta, or En times A, where En is E dot normal vector, which is the component of E that is perpendicular to the surface. So that's what the dot product represents. And so, yeah. But note that with the definition, the electric flux is positive if the electric field lines are leaving the surface, so in this direction, and they are negative if they are entering the surface, so when they're entering here. Well, now we can look at in general where a surface S can be curved, and the electric field E may vary over our surface, so it's not a uniform electric field. But we only care about the case where the surface is closed. So a surface is closed means that it encloses some volume. And so to compute the electric flux, we need to divide the surface into a number of infinitesimally small area elements, which I will denote delta A sub I, and this is a vector. So again, the magnitude is delta A sub I, and we have a normal vector n sub I. So for a closed surface, we want our unit vector n to point in the outwards normal direction to the surface at that infinitesimal area element. So with this, the electric flux passing through each area element would be E sub I dot delta A sub I, which we know is the magnitude and cosine of the theta, which is the angle between the electric field and the normal vector. And now that we have the expression for the flux through one area element, we can derive the flux through the entire surface. And we do this by summing up all of the area elements. So we take the limit as the area elements become infinitesimally small, and this is how you write it mathematically, of the sum of our expression, which is E dot dA, where dA again is our area element. And this can be written as a double surface integral over a closed surface of E dot dA, or to keep it constant, E dot dA. Yeah. So this is the total electric flux. Whoa. This is the total electric flux emanating out of a closed surface S, where E is the electric field and dA is each infinitesimally small area element with some normal vector that is pointing outwards and normal to the surface at that point. So again, To recap, this symbol denotes a double integral over a closed surface, encapsulates some area. And to do this integral, we have to specify our surface and we have to sum the dot products. And so now we can get into our Gauss law. So if we consider some point charge Q, and it is located at the center of a circle with radius r. Imagine that this r, is constant everywhere. I know this drawing isn't accurate, but that's the point. We can look at the electric field first, and the electric field due to the charge is k times q over r square with our unit vector r, which points in the radial direction. And we can enclose this charge using an imaginary sphere of radius r called a Gaussian surface. And so if we have this electric field pointing out, it points out symmetrically over the sphere. And we have again our area element, which is dA. In spherical coordinates, this dA can be written as r squared sine theta d theta d phi with our r hat unit vector. This is a like a given result, but you can search this up online, or I can make a future video explaining spherical and cylindrical coordinates. And of course, we use spherical coordinates because we're working with a sphere. So the net electric flux through the area element is E dot dA, which simplifies to such with our dA. Note that we can drop the dot product because dA points in the same direction as the electric field. So if we look at the definition of the dot product, it would be cosine of theta, which is 0, and cosine of 0 is 1. So yeah, that's how that comes. And then the total flux through the entire surface would then be the double integral over our closed surface S, which is our sphere, of E dot dA, which is we can take this constant out. Everything here is constant. This is the permittivity of free space, and everything else you can tell it's a constant. And we just compute this double integral, which I won't spend too much time on. And that leaves us with simply this. So this is kind of like the more mathematical way to obtain this, but you can also do this if you notice that for a sphere with radius r, the area is 4 pi r squared, and because the magnitude of the electric field at any point is 1 over, this is k q over r squared, the flux would simply be multiplying these two. So multiplying this by 4 pi r squared, and see how this cancels out, this is gone, and you're left with our result as before, which is q over epsilon naught. So this is just an easier way to look at it, or more intuitive way. So in the example above, we chose a sphere to be our Gaussian surface, but it turns out that the shape of the closed surface does not matter. For example, if I have a point charge Q again, and I pick this S1 or S2 or S3, the the electric flux will always be Q over epsilon naught. And so this statement that the electric flux, the net electric flux through any closed surface is proportional to the net charge enclosed is known as the Gauss law. So mathematically, how you say that is, again, the double surface integral over a closed surface S of the field dot dA is proportional to the electric charges enclosed over epsilon naught. So the key thing is that this only talks about the net charge inside the surface, and so the charges that aren't enclosed doesn't matter. So one way you can explain this is that the number of field lines that leave the charge doesn't depend of the shape of the Gaussian surface that we choose to enclose the charge. All right, now here are some steps, some general steps that you can use for doing Gauss's law questions. So firstly, we can identify the symmetry of our charge distribution. So for example, for a sphere, we notice that if we set up a spherical Gaussian surface, the electric field is symmetrical in all parts because it points radially outwards. Um, and then we can determine the direction of the electric field in an appropriate surface, which I kind of just said. And it would be good to have a surface where the magnitude of the field is constant over some portions. And then you would set up your regions and find the enclosed charge of each region, and you find the flux, and then you can equate your flux with your charge in order to deduce the electric field. So now I'm going to do some more examples. We have an infinitely long rod. Imagine we have some infinitely long rod with a negligible radius. So imagine there's no radius, and we have a charge, uniform charge density um, of lambda. And we want to find the electric field at a distance r from the wire, the rod or the wire. So if we use the steps from above, first of all, we want to identify the symmetry. An infinitely long rod has cylindrical symmetry, so the field is symmetrical like such, and so on and so forth. So this is our symmetry. So I can write that down. Then we notice that the charge density is uniformly distributed throughout the length. So the field E must be pointing radially away from the symmetry axis of the rod, which is, the center. Or if we have negligible radius, this is really just the rod. It's the same idea, but if we can draw a better picture. If this is the cross section, then the field looks something like this. Yeah. So these are the field lines. And the amount of charge enclosed by our surface is simply lambda times L, which is the length of our rod. So this is L. All right, so I've put in a diagram of our Gaussian surface. I know this is a beautiful and truly beautiful drawing. So as you can see, I've split the surface up into three regions where we have S1 and S2 being the two ends of our surface, and S3 being the cylindrical walls of the surface. I have the area vectors denoted dA, the electric field at each of these area elements, and also clarified some notation. So, for example, this is L, and this is R. And yeah, we can start a calculation. So we have three parts. So the flux is the integral, which we have three parts. So it's like this. So yeah, this is our expression for the total flux. So I basically split the closed surface integral into three regions, which I've drawn in the image. And we can notice that no flux passes through the ends, which is denoted by these orange lines, because the area vectors dA and dA1 and dA2, they're perpendicular to the electric field, and by definition of the dot product, two orthogonal vectors will have a dot product of 0. So there's no electric flux passing through these surfaces. So we simply have to consider um, the third region, and this, through this whole topic, there's a lot of scary integrals and stuff, but in most of our calculations, it will just be like easy geometry stuff. It's just convention to write it this way. So if we think about it, what we really have here is just they're pointing in the same direction uh, in the way that we set up our Gaussian surface. So that's important. You have to find a good surface to set up so that you have easy calculations. So this is simply the field, magnitude of the field times 2 pi r L, which is the formula for this outer wrapped surface of a cylinder. We can say that E3 is our entire electric field because, again, at the two ends, there's no field passing through them. So now we can apply Gauss's law, which says that our integral, which we computed, is equal to the charge, which is lambda L, divided or times 1 over epsilon naught. Rearranging, we see that this is electric field, and this simplifies. If we cancel r, we get lambda over 2 pi r epsilon naught. Yeah, so that is the total electric field, not flux, because we solved for the magnitude of the electric field. Electric field caused by this infinitely long rod with our uniform charge distribution. So yeah, that's an example of how you can use our steps above to calculate Gauss law problems. But um, now we have another example where we have an infinite plane of charge. So these are all like essential examples you need to know, because I feel like it would be hard to think of what surface to set up for the first few times. So imagine we have some infinitely large non-conducting plate. All right, so this is the diagram for like such. So it is oriented on the xy plane, and it has a uniform surface charge density of sigma. And again, we use our steps. So we notice that this has a planar symmetry, which means that there is some electric field going upwards and some downwards. So now the Gaussian surface we can set up is something known as a pillbox. Yeah, this is our pillbox diagram. This might be a little worse than the other drawing. Yeah, that's beautiful. But essentially, this is our surface on the xy plane. Imagine it lying flat on the xy plane. And we put a pillbox into the surface such that a chunk of it is above and a chunk of it is below. So again, this is a cylinder, so we have three surfaces. It's pretty similar. Two surfaces are pointing outwards at the end, and the other surface is the body of the cylinder. And since the surface charge distribution is uniform, the charge enclosed by the pillbox is simply sigma A, where A is A1 and it's A2. We're only considering this little section of cross-sectional area. So yeah, this is our setup. This is the area of our end caps. And now we can look at the total flux through our surface. Again, three surfaces, we split up our integral. Okay, so the magnitude is the same for surface 1 and surface 2, but this time surface 3 actually has the magnitude of 0, because again, if we notice, the electric field is pointing perpendicularly from our area vector, and again, the dot product of two perpendicular vectors or orthogonal vectors is 0. So we can ignore that, and we have E1 times A1, which is the field pointing this way, with A1, the cross-sectional area, And we can simply do this because, again, these two vectors are pointing towards the same direction. So the dot product simply gives us, um, you know, dot product cosine of 0. So it's simply the products of the two magnitudes. It is the same for the second surface. And we can write this as E1 plus E2 multiplied by A, because A is the same as A1 and the same as A2. So now, because the two ends are the same distance from the plane, no, sorry. So the total flux can be written as 2 times E times A. We can apply Gauss's law now, which says that our integral, or the total flux, is equal to enclosed charge over epsilon naught, and our enclosed charge is sigma A. So we can see that our electric field is simply, after canceling out, we have sigma over 2 epsilon naught. This is the expression for electric field's magnitude. And in unit vector notation, we can say that it is in two components. So this is pointing upwards in the z greater than 0 direction, and pointing downwards in the z is less than 0 direction. We can plot this as such, where this is the z and this is the electric field in the z direction. We have, so we have this graph right here, and we can notice that we have a discontinuity here as we cross the plane, a discontinuity in the electric field as we cross the plane, and the change here is, if we take the top amount minus the bottom, which is a negative number, so it's addition, we get simply sigma over epsilon. And this brings us to our final example of a spherical shell. So imagine we have some spherical shell of radius A, and it has a charge Q evenly distributed over its surface like this. It has an electric field pointing radially outwards from the shell. And the field inside is 0. This has a surface charge density of Q over AS, where AS is the surface area of the sphere. So this can be written as Q over 4 pi A squared. So in this question, we actually have to set up two Gaussian surfaces. So firstly, we have to do some casework. Our first case is like this, where we have a Gaussian surface inside the shell, denoted by this blue surface, and has a radius r. So r is lesser than or equal to a. Now this is our spherical shell with our radius a again, and our Gaussian surface has a radius r larger than a. The charge enclosed by the first surface is 0, since all the charge is located on the surface of the shell and emanates outwards. So we can conclude that the flux is the enclosed charge over epsilon naught, which is 0. So the electric field is 0, where r is less than a. So now we can treat our second case. And now it's a little bit different because we actually have some charge, and charge enclosed is simply Q actually, because we have the entire spherical shell inside, so all the charge is enclosed. So the flux is simply EA, which is the field multiplied by the surface area of our spherical shell. And if we apply Gauss's law, we can see that the magnitude of the electric field is given by Q over epsilon naught times 4 pi r squared, which can be simplified to be 1 over epsilon naught times 4 pi times Q over r squared. And this is actually a constant, which is known as K. This is our expression for the electric field of the Gaussian surface that encloses the spherical shell, such that R is greater than or equal to A. This is our expression. So remember that we have two regions. So if we plot this as E against R, and this point is A, as R, before R is A, we have no charge because this is inside the surface. And at R equals A, we have a jump because at this point the charge is the strongest. Then it decreases quadratically, and this is given by this expression. So again, there's some discontinuity here, which is given by the difference, which is simply sigma over epsilon naught. Okay, so I think that's all the examples I'm going to do in this video, but for the next video, I will probably talk about the example of a non-conducting solid sphere. So yeah, that's it for the electric flux in Gauss's law.